going to talk about the introduction of our project. In this project, we learned that differentiation is the process of finding the rate at which one quantity changes with respect to another. Related rates refer to problems where two or more variables are changing with respect to time and their rates are related through some equations. We can use differentiation to connect the known rates to the unknown rates. With this, we could solve real-world problems involving motion, growth or change, such as how fast a shadow grows, how quickly a balloon inflates, or how rapidly water drains from a tank by finding the rate at which quantity changes over time.
Hello everyone, and now I will be explaining on the Phyla table part regarding question 1. And as you can see here, the Phyla table is divided into 4 columns, each for facts, ideas, learning goals, and actions. So the fact that we got from this question is that the conical tank with a radius of 2 meters and the height of the conical tank is 4 meters, and the water is being filled into this tank at a steady rate of 2 cubic meters per minute. We want to find out how fast the water level is rising when the water is 3 meters deep. And moving on to the ideas where we solve this question, we use the fact that the radius of the water surface changes as the water level rises, because the tank is in a cone shape, so the height and the radius is proportional to each other, and so that the radius of the water at height is r equals to 2 by 4, and times it with h, we get the value for r, which is 0.5 h, and later on we will substitute this into the volume of water in the tank. Depends on the radius and height that we got just now. So V equals to 1/3 by r square h, and substitute the value that we got just now, which is the r equals to 0.5 h, into that formula, and you would get 0.5 h, and later on we will substitute this into the volume of water in the tank. Depends on the radius and height that we got just now. So V equals to 1/3 by r square h, and substitute the value that we got just now, which is the r equals to 0.5 h, into that formula, and you would get the answer about like pi/12 h cubed. And then we would differentiate volume with respect to time to relate how fast the volume is changing to how fast the height is changing. So by this problem, we get that how volume and height relate in conical shapes, and how to use calculus, specifically related rates, to find the rate of change of one quantity when we know the rate of change of another. So the goal is here to find the rate at which the water level rises when the water is 2 meters deep. This rate helps us designing an overflow alarm system, since the water level rises at about 0.283 meters per minute at that depth. So the alarm detects when the rising water is above the given range. So it shows how math and engineering work together to solve practical problems, and yeah, that's all from me.
First, we need to find the radius of the tank when the water is 3 meters deep. So we use radius divided with actual height of the tank, and the radius will become 1/2 height. Next, we replace the r in the formula of the volume of the conical tank with 1/2 h, and the formula will become V equals to 1/3 pi times r squared times h, and we will get the volume is equal to pi/12 times h cubed. Next, we use differentiation to get the rate change of volume by height, and the answer is pi/4 times h squared. After that, use chain rule to get the rate at which the water level is rising, and replace h equals to 3 to get the rate when the water is 3 meters deep.
So moving on to the next part, which is the discussion for question 1. So it overall summarized that this problem involves a conical tank filling with water. So we calculate the water regarding the related terms such as like the time and the volume. So this critical insight is the water's surface radius changing proportionally with its height, and this allows us to express volume in terms of height, and this calculated rise rate is vital for designing an effective overflow alarm, ensuring timely activation to prevent spills.
Hello everyone. In this part, we are looking at how a robotic arm extends its linear segment to reach a target part on an assembly line. Now the facts here is that the arm extension, denoted as x, increases at a rate of 0.2 meters per second. Our task is to find how fast the actual distance d from the base of the arm to the target part is changing when x equal to 3 meters. Now the idea here is that the relationship between d and x may be based on Pythagoras theorem, which is d equal to square root of x squared plus a squared. We are using chain rule from calculus to find the dd over dt. The learning goals is to understand how to apply the chain rule to a function involving square roots. We also need to know how to relate the position and the rate of change in motion. Now the actions we did is we assume a reasonable constant value for the perpendicular distance, as example 4 meters. Then we differentiate d, which is equal to square root of x squared plus a squared with respect to t. And then we substitute dx equal to 3. After that, dx over dt is equal to 0.2 to find the dd over dt.
I'll be explaining the problem and solution for 12.2. So in this problem, we analyze a robotic arm extending its linear segment to reach a target on an assembly line. The extension x increases at a constant rate of 0.2 meters per second, and the total distance from the base to the target is given by the function d equals to square root x2 plus 1. To find how fast the distance d is changing when x equals to 3 meters, we apply the chain rule and find the rate of change of distance with time. So, by differentiate d with respect to x, we get dd over dx equation. And then we substitute dx over dt with equals to 0.2 and x equals to 3. We calculate d over dt, dd over dt, which is the change of distance with time. So we get about 0.19 meters per second. Therefore, the distance from the robotic arm's base to the part is increasing at approximately 0.19 millimeter per second when x equals to 3 meters.
Now for question 12.2, I'm going to explain how this change could impact the robotic arm's positioning speed. The rate at which the distance from the base to the target changes only to negative 0.12 meter per second. But in this case, it has important implication on the positioning speed of the robotic arm. Although the arm is extending at 0.2 meter per second, the actual distance to the target, which determines when the target reaches the part, is changing more slowly due to the angle movement. This difference is due to the angle path of movement. Since the arm doesn't move directly in a straight line towards the target, part of its extension contributes vertically or horizontally, not directly toward the goal. So, although the arm is physically extending at a certain speed, the actual progress towards the part is slower. This is important in automation because it reveals that linear extension does not directly translate into effective reaching speed. Designers must consider the path of movement when determining how fast a robotic arm can position itself.
Down to the conclusion. Through solving problem 12, we deepened our understanding of how differentiation can be applied to real-world situations involving related rates. In question 12.1, we calculated how fast the water level in a furniture tank rises as it fills, which is important for designing reliable overflow alarm system that triggers at the right time. In question 12.2, we determined the rate at which the distance from a robotic arm to its target changes which is essential for maintaining precise control in automatic systems. These problems demonstrate how related rates helps translate constant or known changes in one quality into the resulting change in another, allowing engineers and designers to predict behavior and make informed decisions in a real-life time. Differentiation, therefore, is not just a mathematical tool, it's a practical solution strategy for dynamic systems in fields like manufacturing, fluid dynamics, and robotics. Thanks.